Good evening and a warm welcome present on this platform for session 2 of Conclave 3.0, exploring interdisciplinary intersections, science, social science, and languages. This is a unique webinar series of students organized by IQAC, Olympic College of Arts and Science. It's a pleasure to have with us a young and an apt personality, Dr. Bhargav Alvani, as a chairman for today's session. On behalf of IQAC, I welcome you, Dr. Bhargav. Currently, Dr. Bhargav is working as an assistant professor in computational physics, School of Physical and Applied Sciences, Goa University. He is a product of Goa University, completing his post-graduation in 2013 and was awarded doctorate degree in 2020. His research interest is in theoretical condensed matter physics. He has a vast experience in parallel programming and handling high-performance cluster system and supercomputer. Dr. Bhargav has several publications in reputed journals and was awarded Junior Research Fellowship twice by University Grant Commission in the year 2013 and 2015. With this brief introduction, once again, a hearty welcome to Dr. Bhargav. Before I hand over the session to Chairman, a small announcement to all participants. Feedback links will be posted in the chat box for certificates at the end of the session, so kindly fill the feedback forms. I now request the Chairman to kindly take over the session. Over to you, Dr. Bhargav.
Thank you, Dr. Purnima. And I would like to thank the entire IQAC team for having me as a member for this conclave. Okay. We can start with the presentations, ma'am. I think the first one is Tanay, and first one is Tanay.
I think
You can start presenting. Hello, Tanay. I cannot hear you. I don't know others can hear you.
okay. So can you hear me now?
Now I can hear you. Yeah.
Okay, so I'm Tanay Govigal from FIBAC, DCT is Military College of Arts and Science, Miramar, Nanjing, Goa. And I'll be presenting on Hawking radiation. So Hawking radiation is developed in 1972 and named after the late physicist Stephen Hawking. Hawking radiation basically reduces the mass and the rotational energy of a black hole, and therefore is theorized to cause black hole evaporation. So before we go into Hawking radiation, let's get a brief idea of what is black holes and all the things we'll be needing to go into Hawking radiation. So what is a black hole? A black hole is a region in space-time where gravitational field is so strong that it precludes light from escaping to infiltrate. A black hole is formed when a body of mass m contracts to a size less than the gravitational radius or the Schwarzschild radius. So in a black hole, light cannot escape beyond the event horizon. Beyond the event horizon, nothing can escape from it. The black hole we'll be talking about in this presentation will be only a Schwarzschild black hole, which are non-rotating black hole, and we'll not be talking about the per black hole, which are the rotating black hole, as they get more complex. For simplicity's sake, we're just sticking with the non-rotating black holes. So just to give an idea for scale for how big the radius will be and what mass it will have. For sun, which is having a mass of 2 times 10 to 30 kgs, will have a Schwarzschild radius of about 3 kilometers. While if you were to take Earth and compress it into a black hole, it will have a possible radius of 8.7 millimeters. So how are we going to find the Hawking radiation? Using a semi-classical approach, considering quantum fields around a classical geometry, Hawking realized that the event horizon of a black hole in this possible radius should emit massless particles. So in this, we are going to use quantum mechanics along with Einstein's theory of relativity, from which he was able to prove existence of black holes. Okay, so a bit of a quantum interlude. Quotient momentum uncertainty, also known as the Heisenberg uncertainty principle, states that it is impossible to measure or calculate both position and the momentum of an object. The principle is based on the wave particle duality of matter. So, as we know, you can't know to a 100% certainty the position and the momentum while it is in a wave form. So, but this will not be countered with the thing that if you observe a particle, its wave function will definitely collapse and go to its certain energy state where it will be definite. So, as you can see in the first and second figures, it's about uh, light going through a single slit. Here, the wave shows the density or the probability of finding the particles there. While in the third figure, you can see that there's a interference pattern due to which it has a different kind of a wave pattern with sudden dips and sudden increase in probability. So, what was the whole uncertainty principle of the momentum and time, momentum and cohesion was to get to energy time uncertainty. So, energy uncertainty relation of time and energy is similar to that of cohesion and momentum. Relationship between the time coordinate and the energy implies a well-known relation between lifetime of a state and its energy spread. So, the delta T and delta E is always greater than equal to the reduced Planck constant by 2. So, what do we get by the energy time uncertainty? From that, we understand the existence of virtual particles. So, what a in quantum mechanics allows and indeed requires a temporary violation of conservation of energy. So, one particle can become a pair of heavier particles, so-called virtual particles, which quickly rejoin to form the original particles as if they have never been formed before. So, what you have is starting off with a particle, it just splits off into two particles and then goes back to being the same particle. So, overall, they in the moment there is a violation of the conservation of energy, which is energy can neither be created nor be destroyed, but you can temporarily create it and go back to and destroy it again. So overall, the law of conservation of energy is hold is folded upon. So what do we use Casimir effect? The Casimir effect proves the existence of virtual particles. The Dutch physicist HPG Casimir realized that the zero-point fluctuations of the quantum electromagnetic field in vacuum leads to the remarkable mechanical effect on appearance of long-range attractive forces between two perfectly conducting uncharged parallel plates at a distance L from each other. He calculated this force. So through the energy time uncertainty, we know existence of virtual particles. And to prove the virtual particles, the Casimir effect is an experiment that was performed that proves its existence. In any medium, there is a fluctuation due to temperature or due to the quantum nature of its constituents. In the excitation of a medium, which mediates the effect interaction between the bodies, are massless. The force is long range and nowadays known as the Casimir effect. If the fluctuation occurs in a consists of confined electromagnetic field in vacuum, one speaks of quantum mechanical Casimir effect. So now to actually get onto the main topic, Hawking radiation. All that was done previously was a build-up to finally understand what is Hawking radiation. So in Hawking radiation, you have a virtual pair of photon and an antiphoton formed at the event horizon, such that the antiphoton is within the event horizon and cannot escape, while the photon escapes infinity, and the escape photon is referred to as the Hawking radiation. So as you can see in the figure, the red one is the antiphoton and the white circle is the photon. It is formed such that it has to be formed at the event horizon, which is the circle you can see. The red one is within the event horizon, so cannot escape the black hole and is sucked in. As it is sucked into a black hole, uh, it is made of antimatter, and black hole is made of regular matter. Antimatter and matter will disintegrate each other. So there's a net loss of energy for the a black hole. While the photon is on the outside of the event horizon, so is able to escape to infinity. If it is formed just way beyond the event horizon, they will just form and go back to non-existence. The anti-photon interacts with the black hole made of regular matter. This leads to annihilation of energy within the black hole. So why only a photon? Why not any other particle? The photon does not have any rest mass. Therefore, a photon can leave the event horizon. All other particles having a rest mass and speed less than light cannot escape the black hole. This is the standard model of elemental particles. As you can see, the speed of light that is c is able to escape the just beyond the event horizon, while any other particle will not be able to do so. The properties of Haw- Hawking radiation. Thermal radiation. The temperature of Hawking radiation is inversely proportional to the mass of black hole. That means the smaller the black hole, the hotter its radiation, and the larger the black hole, the lower the radiation it gives out. So, a small black hole will evaporate faster than compared to a larger one. The formula for temperature of a black hole is reduced Planck's constant times the speed of light cubed upon 8 pi g kbm, where g is gravitational constant, kb is Boltzmann's constant, and m is the black hole's mass. Black hole with a mass of one solar mass will have a temperature of about 62 nanokelvins, while a black hole with a mass of 10 billion solar masses will have a temperature of only 6 picokelvins. As you can see, the temperature given off of Hawking radiation is comparatively very low in nanokelvins. Hawking radiation is weak. The rate at which a black hole emits radiation is proportional to the inverse square of its mass, which means that it takes a very long time for a black hole to evaporate completely. So, if you go by the theory of the universe will have a cold end, that will then entropy of the universe will keep on increasing, and all the energy will get dissipated equally. The only thing remaining will be black holes, and the black holes will be the only thing remaining beyond at the end of the universe, which will only evaporate, and then there will be nothing left. For example, a black hole with a mass of one solar mass will take about 10 raised to 64.7 years to completely evaporate, which is much longer than the current age of the universe. So if the universe was to go into a cold death, the black hole will probably outlive the current age of the universe right now. The formula for time, the age of the black hole, time for it to evaporate is m cube times 55120 into pi g square upon 1.8038 times the reduced Planck constant times speed of light cube, speed of light raised to 4. These are the citations and uh, research papers I've used to make this.
Yes, thank you, Tanay.
Yeah,
Hello.
yeah,
You're able to hear me? Yeah.
I'm able to
Thank
hear
you,
you.
Tanay, for this wonderful presentation. You have done it really nicely and systematically. You went through all these points. Um, okay, I had just one query. Okay, that what you showed the temperature in ranges of picokelvin and nanokelvins, right?
Yeah,
So the temperature of these black holes, this thing is really less. But can you tell me the average temperature of the universe, means not near to the star, but if we take on an average the temperature, okay, then what will be the temperature of the entire universe, okay, which is known to us? Do you have any estimate?
I do not have any estimation about it right now.
Okay, it is roughly around 3 kelvins or so, 3 Kelvin or 4 Kelvin, I think. Okay, so these temperature of these black holes and all these really means million times smaller. Okay,
Okay.
that's all. And another interesting thing which you have shown here is the equation which shows the temperature of the black hole. Can you just go to the that slide?
Yeah, yeah, yeah.
Okay, if you look at this equation, I think it is the only equation which we have right now.
Eternal is
Um,
the only one.
yeah,
Or at least
where
what is indicated, which is
yeah,
not totally
all
sure. At least,
yeah, yeah, which is having all the constants which we need. For example, there is Planck's constant which comes from quantum, c cube which comes from speed of light, that is relativity. Capital G is again the gravitational constant, and Kb is from thermodynamics, Boltzmann constant. So it combines quantum physics, relativity, thermodynamics, and gravitations. Okay, so
it is
that's
the
why this
closest approach to
equation.
theory of everything.
Yeah,
Yeah, like closest
uh,
approach to like the theory of everything.
yeah. Yes, yes. Thank you, Tanay. That's all. Yeah,
Yeah,
it was good. Very nice presentation. Yeah.
think so.
If the next person can start presenting. These are Sushil Kumar and Sankalp, I think.
He's sharing first.
Everyone can hear me, right?
Yes, we can hear.
So, this is me, Sunil Kumar Nisar from SYBSC, presenting to you quantum entanglement. Now, what is called like quantum mechanics sometimes look like a weird, like it's like if we go in deeper and deeper, it's like a we cannot find a something. So, but it's a very complicated one. But still, we are having a uh, these are three scientists gave this theory like quantum objects sometimes look weird, spread out like a wave. Here there is a wave, right? In, like a spread out like a wave. Universe seems to be conspires to stop us from knowing every detail of quantum object, and then there's quantum entanglement occurs. Now, so
Uh,
what is quantum
Sunil,
entanglement?
uh, Sunil, I'm
Uh,
not able to see your presentation.
oh, okay, so
Can
so
you
what's the
please
problem?
make it full screen? Something?
Okay, okay. Now you can.
I'm able to see your browser and all of us inside the browser. So I think you can present your screen and keep.
Now,
Now I can see. Yes. Now I can see.
so today's my topic is quantum entanglement. So now, quantum mechanics sometimes look like an assorted, mixed, weird stuff. There's a wave, there's wave particle like here, This like how the waves of particles like waves. Now, where quantum objects sometimes look weird, compact, sometimes like a spread waves, which is here present. Now, where the objects there is a superposition. There is always a superposition for everything. So, where the object seems to be two things at once, says that the universe seems to be conspired to stop us from knowing every detail of quantum objects. And then there's entanglement occurs. Now, Schrodinger says that quantum entanglement is a characteristic trait of quantum mechanics that enforces its entire departure from classical lines of thought. Now, what is superposition? Like, if I give you example, if I give you a box in which a ball is kept, do you know whether the ball is like where, like, what is the position of the ball? No, right? We cannot. So, example is here. Now, here there is a cat. I have kept this cat in a box. Now, I don't know whether this cat, like, if I watch this cat after a week, I don't know. I don't know anything about this cat. If he is dying or he's alive, I don't know anything until and unless I see to this person, this cat. So now, same here. If I keep a cat in a box now, after a week, if I go to see, I don't know anything whether he's alive or died or he gone already. So now, what is a quantum entanglement? Now, imagine two particles. Imagine two particles are electrons which have a quantum property called spin that makes them act like a magnet. If we measure the spin, they are opposite to each other, pointing to opposite to each other in opposite direction. If the one object is like upward, pointing upwards, the other object will be like down, like a gloves. If I give you two gloves in a box, if I give you two gloves, and in one box I kept right hand, and in one box if I kept in left hand. So if I give you one box, if you get a right hand gloves, so obviously you know that the other box will contain a left hand, right? So same thing. So we don't know, and like everything there occurs superposition. Now, so how do we know superposition is real or illusion? Well, one can experimental clues comes from the double slit experiment, which is showing here. The, the experiment shows that the particle is indeed spread out, like they are like spreading out like this. We don't know where the particle is located exactly. So now, if we until and unless we calculate, we measure the position, then only we can come to know that the position of the particles where exactly located, where exactly on the screen it is located and localized. The position we can understand. Now, these are the scientists who proposed, like, who gave the quantum mechanics: Albert Einstein, Boris Podolsky, Nathan Rosen. Without these three people, we cannot understand quantum mechanics. Like, they have given the theories. Now, the more theories yet to come, but these theories are given by these three scientists. Now, Einstein's spooky actions at a distance. Albert Einstein famously described this as a spooky act at a distance where doing something to one of a pair of entangled particles seems to instantly affect the properties no matter how far it is. So now, what this says, now, if I calculate one object, if I have two objects, like one is pointing upward and one is pointing downward. So if I see one object who is pointing upward, so obviously the other object will pointing downward. This is called the superposition of this. So Einstein's famous equation, like famous theory he gave, that is spooky action at a distance. So Neil Bohr says that he proved the theory wrong of the Albert Einstein. There are no hidden variables in quantum entanglement, and quantum entanglement is true. So now, so this is my, like, I have presented. Now I'll handle over to my partner Sankar.
So I'll be doing how objects are entangled. He explained you that quantum particles are entangled. I will explain how they are entangled. So the simplest way to make this is to entangle them from birth. Typically, researchers make pair of photons in a simple quantum jump. For example, when an atom is given some extra energy, it shares it by emitting two photons at once. There are ways of doing this by using lasers, etc. But there are other ways of creating entangle between particles. Another simple way is to simply bring the particle together and let them interact. If you arrange one particle to affect the final state of other particle, then when you put first particle in quantum entanglement, the pair of particles both become quantum entangled. Means the properties are shared. Before the particles interact, we can separate them as their wave functions as particle 1 and particle 2. But once they are interacted, this is no longer true. We can point to any part of the total wave function and say that this is a bit of part 1 and part 2. So once they are entangled, so once they are entangled, you can't say anything without considering the whole wave function. Considering the whole wave function. The property combined, their properties are now spread out over both. This is why it doesn't matter how far apart entangled particles are, they are still joined by their wave function. That is the strange thing. If I have a blue t-shirt, the blue color is localized on there. And if I have a blue mark, the blue color is of the mark, not of the t-shirt. But in quantum, these properties are shared. Some of the blueness of the t-shirt is in the mark. There are some applications of quantum entanglement.
Sankalp, I'm not able to hear you. Sankalp,
For uh, quantum
hello, Sankalp, can you hear me?
Yeah, there are applications of this is that for quantum computing ideas are coming up, and also for quantum teleportation, which you all guys have seen in movies.
Hello, Sankalp.
This is the
You're not about AI actually. Can you come here? Otherwise, come here. Come here. Come here.
Hello, Sankalp. Yeah, Sankalp, you can switch off your camera. It will. Your sound was getting cut and the connection was left.
Bhargav, he is trying to join from the
Yeah, ma'am.
Presentation, you don't want? Okay, presentation you can do from there. Send your presentation. The network you have strong, right? Then put on your microphone for both. Start from beginning. Check from your phone.
I am going to talk about how objects are entangled. He talked about what is quantum entanglement. About how objects are entangled.
You can skip the first three slides, your four slides. I think I could get that much. And then when you said the two particles, simply make them interact. After that, I think you had lost the connectivity. From this slide, you can start.
Third slide. Third slide. Go to the third slide.
There are many applications of quantum mechanics, such as we can make quantum coding. This is the advanced form of coding. We are from binary to quantum coding. And second is that quantum teleportation. You guys must have seen movies, and there are many ideas about this. This is the reference to the link below our YouTube channel.
Yeah, thank you, Sunil Kumar and Sankalp. It was interesting presentation. I must appreciate your efforts in making this PPT. Okay, I just had one small query that when you said that simply make the particles interact, right? If we make the particles interact, you said that they can be quantum entangled. I just wanted to ask you that whether these particles should be um, indistinguishable or it should be distinguishable.
So from starting,
Yeah, I could not hear you. Anyone can answer, Sunil Kumar or something.
the particles can be distinct, but after entangling them, their properties are shared.
Yes, yes. So mainly what we say is that what you are saying is that the particles should be indistinguishable, because if we can distinguish them, then immediately the concept of entanglement fails. Okay. Means we are actually checking that what kind of particle is that. When we are mixing them, it should be indistinguishable particles. And the entire quantum mechanics actually is based on the thing that these particles are indistinguishable. We cannot distinguish one electron from another before measuring. If two electrons are there in space, and before measurement, both are same for us. Yeah, it was a good presentation. Thank you. Yeah, the next one can start. Omgesh Naik.
Am I audible, sir?
Yes, yes.
Can see my screen. My screen is
Screen, check it. There is a presentation. Open the presentation. Share. Share.
building. My screen visible?
Yes.
Okay. So, good morning, everyone. Today I will be talking about the topic Heisenberg's uncertainty principle. My name is Omganesh Sanjay. So, I will be talking about the definition, the one who discovered it was the Heisenberg, the significance of Heisenberg's uncertainty principle, origin of Heisenberg's uncertainty principle, the formula and applications, Heisenberg's gamma ray microscope, Heisenberg's uncertainty principle equations, and numerical applications of Heisenberg's uncertainty principle.
Share the full screen.
Full screen. Wait.
Yeah, make
Enter.
Also put a few there.
Okay.
switch on. Camera with the camera.
Lighting.
Check the screen. Make it full screen.
Full screen.
I repeat. I will be waiting for one who's discovered von Heisenberg, significance of Heisenberg's uncertainty principle, definition of uncertainty principle, common applications, Heisenberg's primary microscope, and Heisenberg's
Still, it is not full screen.
still
One slash.
Hello, Om Ganesh. I'm not able to hear. I don't know if others can hear me.
Dr. Bhargav, can you give us a minute? He lost his connection.
Yeah, yeah, no
We'll
problem.
come
No
back.
problem. No
We'll
problem.
come back.
Yeah, I'm there.
am I audible?
Yes, now you are audible. Yeah.
Good morning, everyone. Today I'll be talking about the topic Heisenberg's uncertainty principle. So I'll be talking about the definition. The one who discovered is Werner Heisenberg. The significance of Heisenberg's uncertainty principle. Origin of Heisenberg's uncertainty principle. Formula and applications. Heisenberg's Camari microscope. Heisenberg's uncertainty principle equations. Numerical application of Heisenberg's uncertainty principle. So, the definition of Heisenberg's uncertainty principle states that it is impossible to measure or calculate exactly both the positions and the momentum of an object, which is based on the principle of wave-particle duality of matter. That is, delta x multiplied by delta p is greater than equals to h dash by 4 pi, where delta x is uncertainty in position, delta p is uncertainty of momentum, and h dash that is equal to h by 2 pi is equal to Planck's constant. So Werner Heisenberg, he it is named after the German physicist Werner Heisenberg, who proposed the uncertainty principle in the year 1927. This principle was formulated when Heisenberg was trying to build an intuitive model of quantum physics. He discovered that there were certain fundamental factors that limited our actions in knowing certain quantities. So what is the significance of the principle? Although Heisenberg's uncertainty principle can be ignored in the macroscopic world, that is, including large objects which can be visible in the naked eyes, the uncertainties in the position and velocity of objects with relatively large masses are negligible. We cannot say that the position of the large objects are wrong. So it holds significant value in the quantum world. But since atoms and subatomic particles have very small masses and actually are not even visible, any increase in the accuracy of their positions will be accompanied by an increase in the uncertainty associated with their velocities. They can be uncertainties in the position in the atoms and electrons which are not visible actually. In the field of quantum mechanics, Heisenberg's uncertainty principle is a fundamental theory that explains why it is not possible to measure more than one quantum variable simultaneously. So, we come across the question, why is it impossible to measure both position and momentum simultaneously? Consider an example where the position of any electron is measured. In order to measure the position of an object, a photon must collide with it and return to the measuring device. Since photons hold some finite momentum, a transfer of momenta, means multiple momenta, will occur when the photon collides with the electron. This transfer of momenta will cause the momentum of the electron to increase. Thus, any attempt at measuring the position of a particle will increase the uncertainty in the value of its momentum. Applying the same example to a macroscopic object such as, let us say, basketball, it can be understood that Heisenberg's uncertainty principle has a negligible impact on measurements in the macroscopic world. While measuring the position of a macroscopic object, there will still be a transfer of momentum from the photons to the ball. However, the mass of the photon is much smaller than the mass of the object which we took as an example. Therefore, any momentum imparted by the photon to the ball can be neglected. The origin of the uncertainty principle. One of the crucial points for the genesis of the uncertainty principle is solely due to the dual nature of a wave particle. Every particle is said to have a wave nature, and the probability of finding particles is maximum where the waveforms are the greatest. If the particle has greater undulation, then the wavelength becomes more indistinct or vague. But the momentum of the particle can be determined. So far, it can be said that the particles that have definite positions will not have fixed velocity. On the other hand, a particle with a well-defined wavelength will show definite or precise velocity. All in all, if an accurate reading of one quantity is found, it will only lead to large uncertainty in the measurement of the other. So, next is Heisenberg's uncertainty principle formula and applications. Let us say if delta x is the error in position measurement and delta p is the error in the measurement of momentum, then delta x multiplied by delta p is greater than equals to h dash by 4 pi. Since momentum p is equal to mv, Heisenberg's uncertainty principle formula can be alternatively written as delta x into delta m into v is greater than equals to h dash by 4 pi, or delta x into delta h dash by 4 pi, where delta h dash by 4 pi, where delta v is the error in the measurement of velocity, and assuming that mass remains constant during the experiment. That implies delta x into delta v is greater than equals to h dash by 4 pi into m. Accurate measurement of positions or momentum automatically indicates that larger uncertainty in the measurement of other quantity. So this implies delta x into delta v is greater than equals to 6.626 into 10 raised to minus 34 by 4 into 3.14 into 9.11 into 10 raised to minus 31, which is equal to 10 raised to minus 4 meters square second inverse. If the position of the electron is measured accurately to its size, that is 10 raised to minus 10 meters, then the error in the measurement of its velocity will be equal or larger than 10 raised to 10 raised to 6 meters or 1000 kilometers after converting from meter to kilometer. Heisenberg's principle applies to only dual-nature microscopic particles and not to macroscopic particles whose wavelength is minimal. So we can conclude that macroscopic particles have minimal wave nature and microscopic particles have can be Heisenberg's gamma ray microscope. That this is the experiment that explains the Heisenberg's uncertainty principle. A striking thought experiment illustrating the uncertainty principle is Bohr's or Heisenberg's gamma ray microscope. That also includes the Bohr's principles to orbit the light ray of wavelength lambda and collect the scattered light in a microscope objective whose diameter subtends an angle theta, as you can see here. This is the diameter, and the angle subtended is the theta with the electron, which is here, as shown in the figure. The precision with which the electron can be located, that is delta x, is defined by the resolving power of the microscope, which implies sine theta is equal to lambda by delta x, which implies delta x is equal to lambda by sine theta. It appears that by making lambda small, that is why we chose gamma ray, and by making sine theta large, delta x can be made as small as desired. But according to the uncertainty principle, we can do so only at the expense of our knowledge of x component of electron momentum. In order to record the Compton scattered photon by the microscope, the photon must stay in the cone of angle theta, and hence x component of the momentum can vary within plus or minus h dash by lambda sine theta. This implies the magnitude of the recoil momentum of the electron is uncertain by delta p of p next is equal to 2h by lambda sine theta. The next question which comes here is Heisenberg's uncertainty principle noticeable in all matter waves? Yes, it's true. The measurement error of any two conjugate properties whose dimensions happen to be joules second, like position momentum, time energy, will be guided by this Heisenberg's value. But it will be noticeable and of significance only for small particles like an electron with very low masses, and not for the large masses such as we took as basketball. A bigger particle with a heavy mass will show the error to be very small and negligible, and vice versa for the smaller particle. So let us discuss about the Heisenberg's uncertainty principle equations. Equation 1 states that delta x multiplied by delta p is similar to h dash, and equation 2 states that delta e multiplied by delta t is similar to h dash, where we discussed about the h dash, which is the value of Planck's constant divided by 2 pi. Delta x is uncertainty in the position, delta p is uncertainty in the momentum, delta e is uncertainty in the energy, and delta t is uncertainty time measurement. So, Heisenberg's uncertainty principle. Let us take a problem as an example. Position of a chloride ion on a material can be determined to a maximum error of 1 mu 1 micrometer. If the mass of the chloride ion is 5.86 into 10 raised to minus 26 kg, what will be the error in the velocity measurement? So solution is delta x is 10 raised to minus 6 meters, that is 1 micrometer. So which is the maximum error in the distance. And after substituting the values in here, delta x into delta m by v into v is greater than equals to h by 4 pi, which is equals to 6.6266 into 10 raised to minus 34 pi upon 24 into 3.14, where 6.626 into 10 raised to minus 34 is the Planck's constant, and after solving this we get 5.28 into 10 raised to minus 35 joules. Therefore, delta V is greater than equals to h by 4 pi m delta x, which is greater than equals to 6.626 into 10 raised to minus 34 by divided by 4 into 3.14 into 5.86 into 10 raised to minus 26 into 10 raised to minus 6, where m is equals to 5.86 into 10 raised to minus 26. After solving this, we get 9 into 10 raised to minus 4 meters per second. we done. So we've seen about what is Heisenberg's uncertainty principle and its founder, Werner Heisenberg. We've seen the significance of Heisenberg's uncertainty principle and also that it is impossible to measure both position and momentum simultaneously in microscopic objects than in macroscopic objects, where the uncertainties in the position and velocity of the same are negligible. We've seen Heisenberg uncertainty principle formula and application, and its use in Heisenberg. We also know that Heisenberg's principle is applicable to all matter waves. Finally, we came across Heisenberg uncertainty principle, equations, and numerical application. Thank you.
And Ganesh, it was a nice and systematic presentation you presented
Yes,
well.
sir.
I just want to ask you
Thank you.
your
Thank you,
views
sir.
in according to you, is Heisenberg's uncertainty principle means the consequences of Heisenberg's uncertainty principle are good or bad?
So it's good because we can predict the position and uncertainties in the position and the velocities of the electrons, which wouldn't be possible without the Heisenberg's uncertainty principle.
Yes, yes. Yeah, that's all I wanted. Yes, thank you. And you answered
Thank
it
you, sir.
well because it sounds very negative as an uncertainty principle, but in actual practice, because our senses are not that means useful to look at these tiny objects, these kind of principles help us to get information about them. Yeah, thank you, thank you. And the next group can present. It is Amisha and Sakshi.
Yes, sir. Hello everyone. Am I clearly audible? Yes, no? Okay.
Yes, you are audible.
Presentation is right. Yeah.
Yes, I can see it.
Thank you. Hello everyone, good day. My name is Sakshi Prabhadesai and I'm here with Amisha Halankar and we'll be taking you to the world of microscopes. Before getting engrossed in looking at the variety of microscopes, I would like to brief you all about the history. So the very first microscope, not microscope as such, it was not at once like the microscope which we have today. It was just simple lens which was discovered by the Romans. And later on the scientists just build up upon the idea and they came up with the microscope which we use today. The lens which was discovered by Romans was a thick lens which had thin edges. Zacharias Janssen and his father made the first compound microscope. As you all can see here, it was a cylindrical in shape. And later on, Anton von Leeuwenhoek discovered his microscope, which was having a plate-like structure in which he observed bacteria, RBCs, and colonies of some yeast and all that. And then Robert Hooke made design modification of the microscope in which he placed a particle-like structures that yielded a lid. Later on, made also modification and he illustrated the microscope which was different so that he can view a more magnified image. And then last, Ernest and Rusker and Maxwell and Ronald came up with his electron microscope, which was very advanced than the lens, which was the first which they observed. Now coming to light microscope, dissecting microscope is one of the simplest one amongst all the microscope. It has a very simple structure. It has two ocular lenses. It is basically used in dissecting and microsurgical procedures. examining archaeological artifacts and geological samples. Then we have the simple microscope, which produces virtual, erect, and magnified image. It is used in cytology study. As you all can see here, we have put a picture of RBCs, which we ourselves had done in the lab. These are our slides. And then we have the working, like how the light enters and the path of the light, which I'll be explaining now. So here there is a light source, like the sunlight. It enters. It first strikes the mirror, and from the mirror, it is reflected to the condenser. Condenser is just basically like you can adjust the amount of light falling on the slide, and on the slide, the specimen is kept which you want to observe. When the slide is placed on the stage, then the light from the condenser, which you have adjusted, will go to the objective lens. And from the objective lens, it will pass through the body tube and near the eyepiece. And from there, you can view the image of the slide which you wanted to magnify and observe the specimen. Then you have the compound microscope. Compound microscope gives us a better magnification up to 1000x. And here there are two kinds of microscope. The first one, which you can see here, is simple. There is one eyepiece, and the other one, it is a binocular lenses. There are two eyepieces, and here the source of light is an LED bulb, whereas in the other, it's normal, the sunlight which enters and strikes the plane mirror, and then, as I said earlier. Then here there are some most common stains which we use. Here we have prepared some slides and all. You can see the xylem, phloem and all. These are the botany slides which we prepared. So the common stains which are used are safranine, Lugol's iodine, and methylene blue. And there are some more. These are the most common stains which I said just now. Then we have the phase contrast microscope. Here, the speciality of this microscope is that you all can view living specimens, like you all can see the movement. You all can study the feeding behavior, the locomotion of a particular organism, and all. And here, there's no need of staining as such. No need to fix the specimen. No need to stain it. Here, you all can see there's some protozoa, which is kept black color. This thing, yeah. Then we have the dark field microscope. Here, there is a lot of specialization in structure, you can say, because the amount of light entering at an angle and all, so that the background is made black and all. Here also there is no need of staining. The structure is such that only the light reflected, refracted by the specimen will reach the objective lens and the image will be formed. As you can see here, the first picture which we have put off the slide is a hydra with a blacked out background. You all can see the hydra. Here there's no need of staining. And the second one is the moena. Here also there is blackout because of the structure of the microscope and the way light enters it and all that. Then we have the polarizing microscope. Here there is a polarizer. When a normal light falls, the polarizer polarizes the light, and the polarized light, when it strikes the specimen, whatever is kept on the slide, it will form such images, very colorful images, and you all will be fascinated just by looking at these images. And these images, which you all can see here, are done by the students of our geology department from our college during the practicals and exhibition. These are the thin sections of rock, and here the color difference is like you all can see different colors, right? This is because of the minerals. Like different minerals will reflect different kinds of wavelengths of the light and all, polarized light. So there's difference in color. Then we have the inverted microscope. Inverted microscope is just like the simple compound microscope. The only thing is that the light source and the light source and the objective lens is inverted. That is the only difference and which makes it unique. It is used in cytological studies and cell division processes, microbiology. Then we have the fluorescent microscope. In fluorescent microscope, it uses the principle of fluorescence, in which a light of higher frequency is absorbed and lower frequency is emitted, so that it gives that fluorescence effect. And a fluorochrome dyes are used in staining these lights. And there are different kinds, different types of fluorescent microscope. One is the confocal microscope. Confocal microscope can give us 2D and 3D images. That is very unique feature of it, you can say. And it has relatively thick specimens which we can view. Then we have the other kind, which are epifocal microscope, multiphoton microscope, and total internal reflection microscope. Thank you. Now I hand over to Amisha.
So without much delay, let's move on to the modern day light microscopes. The first one in the list being the pocket microscope, as you can see in the slide. So from the name itself, we understand that it is a small portable microscope designed such that it can be easily accessible and carried anywhere. The principle is similar to that of a simple microscope. Only thing, you can look at the structure difference. So here the source is LED, which works on a battery like normal batteries that we use in remotes, and it is used by nature observers to during their field trips or field work. So this has a magnification of 250x, and the next one is the foldscope. So in this, it is quite interesting that because this is made of paper, it is a synthetic paper, and you can see in the image how it actually looks like. So it has a magnification of 140x and can visualize bacteria and other microorganisms. And it is claimed to be waterproof. So you can see the slides which are there. We got it from the official site of Foldscope. And the next one is we have the USB microscope and the digital USB microscope. So in this, there's no much difference, but the only difference that is there is like in the USB microscope, there is a cable connection which is provided, wherein you can connect this microscope to your own PC to see the images. And in the digital USB microscope, there is an inbuilt system, like a screen is provided to you. There's a computer software that is provided, wherein you can edit the images, you can take videos and edit them. Here, the magnification in both of this is almost up to 200x. Coming to the scanning probe microscope. So this one, in this, we have an ultra thin probe needle which scans the surface of the specimen and records the interaction to develop an image. So in simple words, we can say that the user cannot really see the atoms or the structure, but the probe feels it and interprets it in the form of an image using a computer. So here the source is laser light, and it is used in basically studying surface chemistry. Coming to the next one and the most advanced one, that is electron microscope. So here, instead of a light source where photons are in the picture, we have this microscope which uses beam of accelerated electrons with very short wavelength as a source of illumination. So it is widely used in biomedical research to investigate detailed structures of tissues, organelles, cells, and also to study microorganisms. As you can see, I put a slide of a bacteriophage here, which we had done during our practical. And now under this, we have different types of electron microscopes, of which TEM and SEM are the most commonly used. Now we will look into what are these TEM and SEM electron microscopes. So the first one is transmission electron microscope, the TEM. As you can see that it is a type of electron microscope that uses transmitted electrons to develop an enlarged image. And here the images that are produced are 2D with very high resolution and magnification of around 2 to 50,000 times. And you can, in the first image that you can see a consolidated structures there which occupies the whole room. So this was the earlier TEM that was there, and now we have come to the new technology where you can see just one table is required to accommodate the whole structure of the microscope. And these are some images taken with this microscope. So next is the scanning electron microscope, the SEM, and here it scans a specimen with a very high energy beam of electrons, and it develops a magnified 3D image. So in the previous one we got 2D images, here we get 3D images. As you can see, these are the pollen grains under SEM. So next is we have a comparison between SEM and TEM. You can have a look at this. It is the same thing. And other electron microscopes are which are there are mentioned, like reflection electron microscope, scanning transmission electron microscope, scanning tunneling microscope, etc. And now to conclude, we can see that right from the first century till now, we have come a long way. It was just one simple lens that was used for magnification then, and now we have such consolidated structures like electron microscopes and technology that is put in that helps us in knowing the life around us, the microorganisms which we never knew before, and now it's possible to study all this life. So I would like to end the session by saying a quote by Robert Hooke. So he said that by the help of microscopes, there's nothing so small as to escape our inquiry. Hence, there is a new visible world discovered to the understanding. Thank you.
Yes,
If you have
thank
any
you,
doubts,
Sakshi.
yes, sir.
Hello.
Yes, sir. Yeah.
Thank you, Sakshi and Amisha, for a wonderful presentation on these microscopes. It was interesting. Many things I didn't know about. Okay, I just had
Yes, sir.
small question that uh, if we want to check bacteria, or if we want to see bacteria, will that paper microscope which you had shown, okay,
Yes.
will that be a good option? Maybe what is the price of that microscope?
Yeah, so that paper microscope, the whole set, if you have to buy, it costs around, it reaches around 2000. If you're buying the whole
Okay.
set, yeah, it is available on Amazon and also on the official site of Foldscope. We had done a research on that. And about the bacteria, we can see
Hmm.
but not clearly, like as in it is like a compound microscope. So the way we view bacteria under compound microscope, we can just see them like tiny balls or something like that. So it is just the same, we
No.
cannot see the structure of the bacteria or something.
Okay. And one more, that electron microscope you had shown, and there you had put one image of one organism, and you said that you have done it in lab. So your lab has that
Yeah, no, no,
electron.
we had a electron micrograph which was shown to us. We cannot do it in our lab because we don't have the microscope.
Okay. 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 That's all. That's all from my side.
Yeah, thank you, sir.
I Yeah, I once again thank the IQAC team and especially Mishkil ma'am and other colleagues of my physics department for having me here for this particular conclave, and all the students have done a wonderful job. Yeah. So it is actually my pleasure to be here and listen to these people.
Thank you, Bhargav, for accepting our invitation and being over here. Yeah, in fact, I found that students have touched the subject which is very difficult by first years or second years to talk about, and they have done their best. What is your opinion about it? Hello, Bhargav. Hello.
Hello, hello, ma'am.
Yeah, you can hear me?
Sound I couldn't. Hello.
Okay. What I said that our students they have really touched a subject which otherwise is very difficult to talk about by our first years and second year students. Actually, it
Yeah,
goes up
yeah,
to
yes,
graduate. And the way they
yes.
have talked about the subject. So, what is your opinion about it? How are our students standing?
Yeah, yeah. Actually, all the talks were really very much interesting, and the way they have prepared the slides and
Yeah.
delivered those talks, Okay, it was actually very basic. Means they have put it in basic words and explained most of the difficult topics. For example, the Hawking radiation, then the quantum entanglement. All these things are really complicated. If we want to tell it to somebody, it becomes really difficult. But the way all of them, means all the presentations have delivered their subjects, is really simple, interesting, and they've made things more curious. Okay, and if they are doing it at this first year and all, I am sure that they are very much enthusiastic about taking science. Okay, and
Yeah,
they are doing a good job. Already they are doing good job.
yeah, yeah. Thank you very much, Dr. Bhargav, for being
Yeah,
with us.
thank you,
And
ma'am. Yeah,
Purima, you can take over.
yeah. I will congratulate actually the IQAC team and all the teachers and mentors who have um, uh, made this event and encouraged the students. It was a really great initiative, ma'am. Yeah.
Thank you, Dr. Bhargav, for your expert comments. Before I go to vote of thanks, just a reminder to the participants that feedback form has been posted in the chat box. So kindly fill the form so as to get the certificates. On behalf of IQAC, I extend my gratitude to Dr. Bhargav for chairing today's session and giving his expert and valuable comments to our students. I also thank to our respected principal, Professor Vrinda Borkar, for her immense support in organizing this webinar. Today's session would not have been possible without teachers' guidance. So sincere thanks to Dr. Mishkil, Dr. Shilpa Bhosle, and Dr. Kapil Salkar for guiding their students so excellently. Thanks to all the speakers of today's session for their excellent and informative presentations. These were our FY and SY students. It's not very easy to present on this platform. So we are very proud of you, dear students. For social media publicity and technical support, I thank Dr. Chandan Naik and Mr. Gaurang Bane. And lastly, a big thank you to all the participants for being good listeners. Once again, thanks to one and all. Have a great day.